So far, we've considered objects that move at constant velocity. But in the real world, the velocity is almost always changing. Things speed up, slow down, and change direction all the time. For instance, an object falling to the ground, a car going around a curve, a spring oscillating back and forth, and even the Earth going around the Sun are just a few examples of systems that experience acceleration of one type or another. So to quantify the rate of change of velocity, we define this new quantity, which we call the average acceleration. And symbolically, we can write that the average acceleration is equal to the change in velocity divided by the change in time. As always, we can translate this into a mathematical equation by writing A equals to delta V over delta T. And first of all, we need to settle the units. Now these are units of velocity, which is meters per second, divided by units of time, which are second. And when we combine these, we get units of meters per second squared. These are the standard units of acceleration in every textbook. Now, just like velocity, acceleration is also a vector quantity because it's given in terms of the change in velocity. Now, the effect of acceleration is to change the velocity over time, and it can do this in three different ways. It can either do it by changing the magnitude of the velocity, by changing the direction of the velocity, or by changing both the magnitude and the direction at the same time. Now, the effect depends on the relative sign between the two, or more precisely, the direction. If they both point in the same direction, then the acceleration increases the velocity. If they point in opposite directions, then the acceleration decreases the velocity. Let's consider one example. Let's say that an object is moving in a straight line with increasing speed. We're going to label the initial velocity at time t initial by v initial, and we draw the vector that points along the positive x-axis. Then, at some later time t final, the velocity will have a different value, v final, which will point still along the same direction, but it will be a longer vector because now the magnitude of the velocity has increased. Then we notice that there is a change in velocity, delta v, which is v final minus v initial, which points still in the same positive direction. That's because the direction hasn't changed, but the magnitude of the two vectors has increased, and therefore their change, represented by that green arrow, is just the difference of the two vectors. Now, this change in velocity takes place over a finite amount of time, delta t, which will be t final minus t initial, regardless of what t final and t initial are. And therefore, from this we can see that our acceleration, which is proportional to delta v, and therefore points in the same direction as delta v, is also pointing along the direction of increasing v. So this is the case in which the acceleration points in the same direction as the velocity throughout, and therefore the tendency of the acceleration over time is to increase the magnitude of the velocity without changing its direction. Now the same argument is true for the other cases, and from the table here we can notice that when the sign of the velocity is the same as the sign of the acceleration, then the effect of the acceleration is to increase the velocity, whether both of them are positive or negative depending on how we define them on the axis. It's only when the sign of the acceleration is opposite to the sign of the velocity that the effect of the acceleration is to decrease the speed, therefore the magnitude of the velocity, as it's denoted by the vectors on the right. So make sure you study this table because it gives you the four different possibilities. Now, as I mentioned earlier, we're not considering the case in which the acceleration is perpendicular because that requires a separate analysis which we'll tackle in a separate video. So let's do an example. A Formula One car can go from 0 to 31.6 meters per second in 5.9 seconds. A, what is the car's average acceleration? And B, if the same car can come to a complete stop from 20 meters per second in 2.25 seconds, what is its average acceleration? And notice that I said mind the sign. So as always, you should stop the video right now, attempt the problem yourself, and then come back. Assuming that you've done that, let's go over the solution. So for part A, what's given to us? In part A, we know that V initial is 0.0 meters per second. And notice that I put the units there even when the quantity is identical to 0. That's always good practice. The final velocity is 31.6 meters per second. And this change in velocity takes place over a time interval of 5.9 seconds. Therefore, we can calculate the average acceleration through the formula as delta V over delta T. Delta V is going to be V final minus V initial divided by delta T. And in this case, this is 31.6 meters per second minus 0 meters per second, all divided by 5.9 seconds. Now clearly the 0 doesn't contribute, and when you plug in the numbers, you get 5.36 meters per second squared, rounded to 3 sig figures. Now this example here, it's identical to the example that we analyzed earlier, in which the velocity is increasing along the positive direction, and as we can see, the value of the acceleration is also positive because it points along the same direction as the velocity. And so its tendency is to increase the magnitude of the velocity. Now in the second case, we're told that the car comes to a complete stop from 20 meters per second in 2.25 seconds. So we have to be careful with how we label things. So for part B, the car is actually initially moving at 20 meters per second. And because it comes to a stop, the final velocity is now 0 meters per second. And delta T is 2.25 seconds. So we find the acceleration by using the same formula, of course, but now V initial and V final have changed, and we plug in the numbers. So we get 0.00 meters per second minus 20 meters per second all over 2.25 seconds. Now in this case, the final velocity is 0, the initial velocity is 20, and therefore the numerator is going to be a negative number. This is going to be negative 20 meters per second divided by 2.25 seconds, which gives an acceleration of negative 8.89 meters per second squared. So why is the acceleration negative in this case? Because the tendency of the acceleration in this case is to slow down the object. If we draw the vectors as we did before, the object as a time t initial will have an initial velocity, which is this one here, and later on at some time t final, which is 2.25 for us, the car is here, but its final velocity is 0, so it's the 0 vector. For that to happen, there has to be something that shrinks the initial vector to 0. And for that to happen, there has to be an acceleration that points in the opposite direction.